In 4.5, our objective is to integrate composite functions using the substitution method. Now that can be kind of tricky, and therefore it would be nice to have some ways to make our work not as complicated. So we look for shortcuts. So a couple of the shortcuts that I want to remind you about before we start the tricky stuff is when a function is even versus when a function is odd, and the kind of shortcuts that we have there. When a function is even, remember what that means. It graphically reflects over the y-axis. So an example could be something like y equals x squared, and we know graphically that's a parabola. If I were to, say, take the integral from -3 to 3 for x squared with respect to x, that means I'm finding the net area that is created between the function and the x-axis on the interval -3 to 3. So it's finding this net area right there. So because of the symmetry, we know that whatever we have on this side of the y-axis is exactly the same as what we have on this side of the y-axis. Therefore, instead of doing the antiderivative and plugging in the top limit and the lower limit, we can say instead, how about we just integrate half of the way, 0 to 3, and then we double it. Well, we still have to do antiderivatives, but here's the nice part. We don't have to plug in a negative number anymore, and we get to plug in 0, which makes a lot of things disappear. So think about that for an even shortcut. Odd functions. Those rotate about the origin, or we can think about them as reflect over both axes. As an example, y equals x cubed. Let's look at a picture of an odd function like y equals x cubed, and that's going to be something like that. So if we're taking, for example, the integral from -3 to 3 of x cubed dx, that means from here to here, I'm finding the net area of what's bound between the function, notice touching the function, and the x-axis. So that's going to be this area in here. Well, remember, those are exactly the same areas, so they cancel out, and it's just 0. So as we start to get into the tricky u-substitution rule, remember some of these shortcuts that are going to make it easier. So again, here is our goal for today. We want to integrate composite functions. What is a composite function? Let's take a step aside from this for a moment and remember what is a composite function, like f of g of x, where we have a function inside another function. For example, let's remember back to when we did derivatives. Let's say we have y equals the sine of x cubed. Instead of just y equals the sine of x, we have more than just x inside the sine function. Well, remember that when we do the derivative of a composite function, we have to use the chain rule. We do the derivative of the outside first, so this turns into cosine, while the inside stays the same, and then we say times the derivative of the inside, so times 3x squared. We used the chain rule. Well, now we're going backwards. So if we have cosine of x cubed, this is what we say today. Let's say that if dy dx is cosine of x cubed, how am I going to go backwards? Well, to end up back where I started, I have to have this 3x squared in there because that's where this came. That's where this started, is sine of x cubed gave me cosine of x cubed times the derivative of the inside. So if dy dx is this, then I can go backwards, integrating both sides. This becomes y equals the antiderivative of cosine of x cubed times 3x squared with respect to x. So here's what I want you to see in this. If we are going to integrate a composite function, this is a composite function, because there is a function inside another function, I have to have the derivative of that inside function in my integrand. So this is the derivative of the inside. This takes us to the substitution rule. So back to your notes. How are we doing the antiderivative of a composite function? This is what you need to see. The antiderivative, or the integral, of f of g of x has to have the derivative of g of x multiplied to it. The derivative of the inside has to be multiplied with respect to x. Then we can take the antiderivative of f, capital F, and of course, don't forget the constant. So remember that we want, if we have a composite function, the derivative of the inside multiplied to the function. The derivative of the inside needs to be there. Now, there's a lot of ways to do that. I like to do it in precise steps that will work no matter what, anytime. There's a lot of ways that you'll see some people do this. I'm going to show you one way that'll work all the time. So in number one, I notice we have a composite function. How do I notice we have a composite function? Composite means a function inside another function. So think of that. Composite means function inside another function. That's the f of g of x deal. So look for parentheses. Look for anything that's creating a group of some sort. Radicals create groups. The trig functions create groups. Denominators create groups. That's where you're going to find that you have a composite function. So here I have parentheses, a function that is raised to the fifth. This is the inside function. So the first thing we're going to do is identify what is the inside function, because that needs to be how we determine that the derivative of the inside function is also there. So first thing we do is determine what is the inside function, and I like to call it u to simplify. So u equals x squared minus 9. That's our first step. Let u equal the inner function. Next, remember that we need the derivative of the inside function in our integrand. So we have to know what is the derivative of the inside function. Therefore, the next step is finding that derivative. So after we have u, if this is in terms of x, we find du dx. So the derivative of this, 2x. So our second step, find du dx. Now, I see that the derivative is 2x. So I can say, hey, I have the derivative there. Now I can either kind of just ignore it and say, let's take the antiderivative of u to the fifth, but these problems aren't going to stay this simple. So let's find a strategy that works every time. Here's the strategy that will work every time. If I can substitute this for u, I want to substitute everything that has an x in it in terms of u. So instead of having du dx equals 2x, I'm going to solve for dx. I want the dx to not be there. If this is going to be u, I want to change what follows to be du. So my next step is solve for du. I'm going to multiply both sides of this by dx, so that dx ends up over here. And then I'm going to divide by 2x. So dx ends up equaling du divided by 2x. So multiply by dx, divide by 2x. So du over 2x equals dx. So third step was solve for dx. How does this help? Well, if this is dx, I don't want it to be dx, I want it to be in terms of u. So this will say instead du over 2x. Look at what we have after we've done that. The du is there instead to match the variable u, and the 2x cancels out from in there because that's the derivative of the inside. That was part of du dx. Now that's gone. So we rewrite the integral so that it's just in terms of u. So instead of this stuff with x, we write u to the fifth. Everything here, what's left over? Du. So our fourth step, we plugged in to the integral to write everything in terms of u. So the u and the du is all that's left. We plugged in what we solved for. We plugged in what u equals, and we plugged in what dx equals, and that got us to just stuff with u. Then we can integrate, because now this is just a simple power function. So step 5, we will integrate, or take the antiderivative. So the antiderivative of u to the 5th is u to the 6 over 6, of course, plus c. And finally, because the question gave us in terms of x, we give our answer in terms of x. So finally, we plug back in terms of x. So basically, that's putting the inner function back. What we took out to call u, we put it back. So what I said u equals, that goes here. So instead of u to the 6, x squared minus 9 to the 6th over 6 plus c. Let's try a few more. I'm going to pick up the pace a little bit, but to see some different scenarios of the u-substitution method. First, we determine what is the inner function. This says the 6th root of 3 minus 8x. So the stuff that's in the radical is the stuff that's in our group. So that's what we call the u. U is 3 minus 8x. What do we do after we've identified the u? We solve for du dx. The derivative is negative 8. Then we need to get the dx out and the du in. So we get the dx by itself, multiply by dx, divide by negative 8, that's du over negative 8. Then we can substitute it in here, du over negative 8. Let's see how that works out. We've got a negative 8 up here, a negative 8 down here. Let's write what's left over. Integral of the 6th root of u times du. Well, this we can integrate if we just change it to the integral of u to the 1/6 du. Use our power rule, u to the 7/6 divided or multiplied by the reciprocal, divided by 7/6 means multiplied by 6/7, put plus c, and then finally substitute back what u equals. So we never leave it in terms of u if the original problem wasn't in terms of u. There we go. 3 and 4 look like trig functions. The inside of the trig function sometimes is the u. What I want to think to myself is, what is the trig function I see? Do I know the derivatives of the trig functions? Because that's really going to help me to determine what is my inner function and what is the outer function. So I see a secant squared here, and I think to myself, is there a function whose derivative is secant squared of u? Yes, there is. The derivative of the tangent of u gives secant squared of u. In number 4, is there a function whose derivative is sine squared of u times cosine of u? No, there's not. So let's look at this one a different way. Is there a function whose derivative is sine squared of u? No, there is not. So let's look at this a different way. Is there a function whose derivative is cosine of u? Yes, there is. It is the sine of u. Well, notice that we have a sine function in here, a sine function and a cosine function. In fact, if we rewrite this problem so that the squared is not here, but like this, you can see a little bit better what probably is the inside function in number 4. The inside function for number 4 is all of this function that's being squared, because guess what? Its derivative is cosine, which is what we see here. Let's walk through this problem since we've been working on it, and then we'll go back and look at number 3. So the u is the sine of 3x. We have to solve for du dx. This is a chain rule, so we have the derivative of sine is cosine of 3x, but then the derivative of 3x is 3. solve for dx, so get dx by itself, divide by 3 cosine 3x, and we have du over 3 cosine 3x. Let's plug that up here, and that would have been helpful if I had written the dx. Now let's plug that in there, so dx instead is du over 3 cosine 3x. Notice what happens, what should happen, because the derivative is in there, it cancels out with that, but the 3 is still there. Actually, it's a 1/3. Pull it out because it's just a constant multiple. Now let's rewrite. 1/3 outside, integral. All of that became u, and it's u squared, and what I have left here is du. Let's do the antiderivative. 1/3 on the outside, u cubed over 3 plus c, and plug it back in. We don't want to end with u in our answer, so 1/3. Actually, we could multiply our 3's in the denominator, make 1/9. The u is sine of 3x. That's all to the third plus c. Good. If you want to rewrite it with the exponent there, that's good too. Let's go back to number 3 and see how it's a little bit different. So because we have a derivative of tangent to be secant squared of u, that means we don't want to think of this as secant of x to the 6 squared, like how we thought of this as sine to the 3x squared. We don't want the squared to not be there because the derivative of tangent is secant squared. So instead, the inside of the secant function can be our u. So let's say u is x to the 6th, then you know what comes next, du dx. 6x to the 5th, and then we have to solve for dx. So dx, multiply by dx, divide by 6x to the 5th, du over 6x to the 5th. Plug it back in up here, du over 6x to the 5th, and now simplify as much as we can. That becomes u, x to the 5th, cancels with x to the 5th. I have a 6, let's not forget about that. We can pull that out. So rewriting 1/6 integral secant squared of u, and du is all that's left. Remember the antiderivative of secant squared of u? Tangent of u. So this becomes, when we do our antiderivative, 1/6 tangent of u plus c. Don't leave it with the u. U is x to the 6th. So 1/6 tangent of x to the 6th plus c. Here's another scenario where we have a grouping, looks a little bit different than the other ones. This time, notice what's in the parentheses happens to be part of what's in the denominator. So our u will be that part. Why don't you pause the video here, give it a shot, come back, and see if you've done it correctly. All right, let's check in. Our derivative, 4x cubed, solve for dx, du over 4x cubed. Plug it in, du over 4x cubed. X cubes cancel out. The 5 and the 4 doesn't, but those we can bring outside. 5 over 4, integral. Nothing on top but 1 u squared on the bottom, and du. Of course, we need to rewrite this, u to the -2 du, and then we can do our power rule. 5/4 u to the -1 over -1 plus c. Rearrange it, so -5 over 4u plus c, and then don't leave it like that. Substitute what the u is back. -5 over 4, the u is 1 plus x to the 4th. So you wrote what it is here, and don't forget about plus c. Yay! Now, here is one that is going to do something a little bit different. I see a radical. I know that that's a composite function because there's stuff inside the radical. So going about our normal steps, we're going to take u to be that stuff that's in the radical. Going about our normal steps, we're going to take the derivative of that stuff, -3. Going about our normal steps, we're going to solve for dx, du over -3. Going about our normal steps, we're going to take out dx and put in du over -3. What do you see that's different here? I can't get rid of this x. It doesn't cancel out. That means the derivative is not there only, but I have more x. And here's what we'd have so far if we substituted. Of course, I can pull out this -3. So I can write this as -1/3 times the integral. I have x here still, and I have the square root of u, and I have du. Here's the problem. We can't mix x's with u's. We cannot take the derivative, antiderivative, while there are two different variables here. We're trying to take it with respect to u. So I have to make this x go away. How can we do that? This is how. Look at what we called our u. We defined it as 1 minus 3x. Use our u to solve for x. If u equals 1 minus 3x, we subtract 1, we divide by -3, and now we know what x is in terms of u. We can rewrite it if we want to be a little bit prettier, maybe -1/3 times u minus 1. But either way, we know what x is. So we're going to take out the x, and in its place, we're going to put what we found that it equals. So let's rewrite our integral, -1/3 integral of, so instead of x, we're plugging in everything that x equals. -1/3 times u minus 1, and I'm going to rewrite this to u to the 1/2 because I know I'm going to be taking the antiderivative. I need to use the power rule. Now, I'm not ready to take the antiderivative because I still have a product of u's. I cannot take the antiderivative with a product. So I'm going to distribute. And by the way, this is just a constant multiple. We can bring that guy out to join with that constant multiple, simplifying a little bit. So this becomes +1/9 integral. U to the 1/2 times u to the 1 is u to the 3/2. U to the 1/2 times 1 is u to the 1/2. Now we can do our antiderivative of each of those terms. So we do that, 1/9 on the outside, u to the 5/2 times 2/5 minus u to the 3/2 times 2/3. Put your plus c at the end somewhere. Finally, don't forget to plug in what u is before you say I'm done. So 1/9, 2/5. Let's go back and find what is u. 1 minus 3x. So 1 minus 3x to the 5/2 minus 2/3, 1 minus 3x to the 3/2 plus c, and there we go. And just because it's a little bit crowded, I'm circling my answer.